Hi everyone. In this video I'm going to be talking about the two-sample t-test and just going over one example of the two-sample t-test. Now, the first thing to know about the two-sample t-test is when we say two samples, we're talking about two independent samples. So this is different from the paired t-test, where each observation in one of the samples has a corresponding related observation in the other sample. But again, here in the two-sample t-test, we're just talking about totally independent samples. And then the other thing I wanted to remind you guys about this test is that the parameters of interest are the population means of the two groups. So we have two populations, they have their own mean, each one does, and we're interested to know, are those two population means equal? Are those two population means not equal? And so that's just the null and alternative hypothesis for this test. So let's take a look at the example problem here. This is from your book, and I picked it because it is about the periodical cicadas, who I love. My children kind of hate them, but I love them, and just for everyone's enjoyment, I'm gonna show you a picture of them. So here's a picture of one of these guys. They are so awesome. This is Brood 10 is the one that came out in 2021. They come every 17 years. For those of you who are international students and maybe weren't here in 2021, it is a whole phenomenon. There are so many of them. They're all over the place. And it's just amazing that they only come out every 17 years. So that was my third time in my life seeing them, and I love them. My kids weren't so impressed. So that's what they look like. So the idea for this problem, and maybe I can just go ahead and delete this guy for you guys. The idea for this problem is the researchers were measuring the hind tibia lengths of the shed skins of 110 individuals. So that's the other thing about them. They come out of the ground and then they shed their skin and they leave their skins all over the place, and it's a big mess. So they're looking at the tibia lengths on the skins that have been shed, and they're comparing males versus females. And for each group, they are measuring those tibia lengths, and then we have some sample data on the two groups. Now, sample size for each group, 60 and 50. If you're worried about being able to know whether it's paired data or not paired data, one immediate clue is if you have different sample sizes, the data is definitely not paired. But there's no pairing here going on. We have two totally separate groups, the males and the females. And in each group, we have come up with the sample mean. So this one here is Y1 bar, and this is Y2 bar. And then we also have the sample standard deviations. So I'm calling this S1 and I'm calling this S2. Now, we stated the null and alternative hypothesis on the previous slide, so the next thing we need to do is go ahead and formulate our test statistic. The test statistic for the two-sample t-test looks like this. It is Y1 bar minus Y2 bar over the standard error of Y1 bar minus Y2 bar. So we have Y1 bar and Y2 bar. They're in the table, but we do need to calculate the standard error of Y1 bar minus Y2 bar before we can finish off the test statistic. So I'll do that over here on the right. The standard error of Y1 bar minus Y2 bar for the two-sample t-test looks like this. S2 squared over N2. And just as a reminder, this is N1. This is N2. And so we'll calculate this as the square root of 2.87 squared over 60 plus 3.52 squared over 50. And my calculations tell me that that is 0.62056. So now we have what we need to go to actually compute the test statistic, which looks like 78.42, that's from here, minus 80.44, divided by this 0.62056, and that comes out to minus 3.26. So we have the value of the test statistic. All we need now is to know what we're doing when we get to the table, and that requires knowing the degrees of freedom. For the two-sample t-test, there are a couple of different ways of estimating the degrees of freedom. I'm on a test always going to give you guys the degrees of freedom, or else give you the very simple formula for the degrees of freedom, or estimate of the degrees of freedom, which looks like this. This is just an estimate, but it's a decent one. So for this problem, it's 60 plus 50 minus 2, which is 108. And again, it's just an estimate. So when I go to the table, for that high number of degrees of freedom, I'm going to find that the closest value, the closest degrees of freedom in the table is 100. And so that's okay to use that. We're just using an estimate here. Okay, so I'm going to rewrite the test statistic up here. That was the test statistic TS equals minus 3.26. And we also said that we estimated the degrees of freedom to be about 100. So we go down in the table and find where the degrees of freedom is 100. That's this row here. And we're looking at where the absolute value of our test statistic lies in that row. So with my test statistic at minus 3.26, I'm looking for 3.26 on this row. And if I zoom in a little bit here, you can see it's going to be between these two guys, 3.26 is. And that means that the upper tail probability is between these two values. So what I'm ending up with is that the upper tail probability is between 0.0005 and 0.005. That's just the upper tail probability, and since my null hypothesis didn't say anything about less than or greater than, and neither did the alternative hypothesis, we're just looking at whether the two population means are equal or not equal. That means we're using a non-directional test, and since the probabilities in this t-table just give us the upper tail probability, we need to actually multiply these values by 2 so that we're considering both tails of the distribution. So really, my p-value is going to be between 0.001 and 0.01. I'm just multiplying the values in the inequality above. Assuming that we're using the typical alpha equals 0.05 for our hypothesis test significance level, then we can see that the p-value is definitely less than alpha, meaning that we can reject the null hypothesis and that we do have evidence that the two population means are different. That is, we do have evidence that the tibia lengths of female cicadas are different from the tibia lengths of male cicadas.